All right, let's get started. So this is the second lecture on machine learning. And the question we're going to start out with today is, can we obtain decision boundaries, which are circles, by using linear classifiers? So remember last time we talked about linear classifiers and what kind of classification boundaries they might be able to allow us to represent. And now the question is, can we do something like circles? Okay. So you might not know the answer. Just kind of use your judgment, and I'll get a report. We'll come back to this in the later half of this order. So a lot of you said 550? There aren't that many people here. Okay, maybe I think I forgot to reset. So this includes last year's, I think, too. But anyway, so a lot of you said yes. And if those of you who think this is a trick question, you're right. It is a trick question. And we'll come back to this later in the lecture. Oh, so the answer is yes, by the way, which seems a little bit strange, right? OK, so let me review what we've done so far. So we're talking about machine learning. And at a very high level, what machine learning is about is taking a training data set, feeding into a learning algorithm, which will then output a predictor. And this predictor can take new inputs, x, and output new outputs, y. Okay? And last time we talked about the learning algorithm as setting up as a kind of optimization problem, and then using an optimization algorithm like stochastic gradient descent, or SGD, on this. So let's poke into each of these boxes a little bit more. So this is all review. So last time we talked about what is our objective function. Our objective function is to minimize the training loss with respect to a weight vector. And this training loss is the average over the losses of individual examples. So loss x, y, w, remember, is how much loss, how unhappy we would be if we used a predictor based on w to predict on input x when the true answer is y. Okay? And what we want to do is to find a single weight vector that tries to fit all the data, basically obtain low loss kind of in aggregate across all the data points. So peering inside, double click on loss. We talked about different types of loss functions for different purposes. So we talked about regression, where the goal is to predict a number, for example, housing price. And we also talked about classification, in particular binary classification, where the goal is to predict a discrete label like, is it positive or negative? So is it spam or not spam, for example? Okay, and we had these plots, which is something to kind of stare at for a while. So the loss function, remember, is trying to capture properties of the desired predictor. So in regression, we looked at the residual, which was our prediction, which is the score, minus the true answer. This is how much we overshoot. And if the residual is 0, then we would pay 0 loss. As the residual goes away from 0 in both directions, we pay some sort of cost, either quadratic or absolute value, depending on the type of loss function we choose. For binary classification, we looked at the quantity called the margin, which is the score times y. And this measures how correct we are. And the more correct we are, the less loss we pay, sometimes 0. And if we're wrong, which means negative margin, we're going to be paying a loss. So last time, remember, we looked at the 0 or 1 loss, which was, in some sense, the loss we care about, but it was difficult to optimize. So we looked at these surrogate loss functions like the hinge loss and the logistic loss. And we'll come back to kind of exploring some of these loss functions in more detail later. Okay? Okay, so with these loss functions, remember we form, actually one thing that I thought might be useful is to kind of do a quick example. This is also in the notes, but just to kind of ground things out a little bit. So suppose we're doing regression. So I'll do a little example here. So suppose we're doing regression, and we have our data points, which are, let's see, 1, 0, that's x. And what's y? Let's say it's 2, 1, 0, you see a 4, and 0, 1, you see a -1, okay? So pictorially, what this is, now I'm plotting x1, x2, so we're doing two-dimensional regression, which means that for every point in the plane here, I'm going to have a predictive value. So I want it to be the case that if I have 1, 0, I'm going to have 2 points sitting there. which sometimes there's noise in our data. So sometimes you get a 2, sometimes you get a 4 at that data point. And here we have a -1. So our label here is -1. So what we want to do is fit a function. I can't really draw in because it would be 3-dimensional, but for every point we need to predict some value, and we're told that this one we'd like to be -1, this one we'd like to be either 2 or 4. Okay, so now let's translate this prediction picture into the loss minimizing picture. So let's suppose we're doing loss minimization with a quadratic loss or the squared loss, which means that we're going to be trying to find the wave vector. So how many wave vectors are there? Well, there's one wave vector. How many components does it have? Because it has 2 components, W1 and W2, because we're in 2 dimensions. And we're going to average the loss of the individual examples. So 3 examples, each one is going to contribute to a loss. And the first point is 1, 0. Let's do it this way. So W dot the feature vector, which is 1, 0, minus 2 squared plus W dot 1, 0, minus 4 squared plus W dot 0, 1 minus -1, so that's a +1 squared. Okay, I'm out of space, but you should round out the parentheses. Okay, so this is the training loss. So this is, so this whole thing is the train loss. And we want to find wave vectors that minimize this, okay? So just to kind of, let's try to simplify this a little bit. So this is going to be 1/3. So W dot 1, 0 is, how can you simplify this? W1 minus 2 plus W1 minus 4 plus, and what about this one? W2 plus 1 squared, okay? So this is the objective function. And if we want to plot it, what it looks like is as follows. So now we're plotting W space, W1, W2. And now this is a little bit hard to plot, so I'll kind of try to wave my hands on the board here. So if you look at this term, what does this want? This wants W1 minus 2 squared to be small, which means that it wants W1 to be close to 2. Okay, so let's look at, so here's 2. So if you look at this term in isolation, and you look at the level curves, it's going to be something like, okay, I get 0 loss if I play wave vectors here, and I'm going to get more increasing loss as I go out, right? Okay, if you look at this second term, it's centered around 4. So here's 2, here's 4, and it's going to be kind of the same deal. So, I'm going to get 0 loss here, and I'm going to, pay more loss as I go out. Okay, now what about this one? So here's -1. This term wants W2 to be -1. It doesn't really care what W1 is. And so it's going to be some sort of level curves are going to be like 0 along here, and then think about a parabola like this coming out of the board. Okay, so you have these 3 parabolas, and you're summing them together, and that's your objective function. Right, so remember, you have to find a single setting of W1, W2 that, on average, minimizes the loss over all the data points. Okay? So now, if we go and try to actually figure out what the objective function looks like, where do you think it will have its minimum? 2, -1. That would be the case if we didn't have this term, but there's a 4 pulling here. So 3, -1. Yeah, so you can solve this explicitly, but intuitively it should be there. And the level curves are going to be something like this. Okay? So any questions about this? So we picked a kind of a very simple problem. We're getting points, and here is a kind of a loss picture. Yeah, question back there?
Why the intuition is that you can directly see that it's minimum at 3, -1?
So the question is, why can you see directly that it should have a minimum of 3, -1? In general, you can't. One answer is that if you do the foundations homework, you'll find out why it would be here. The other answer is that, well, intuitively, this term just wants W2 to be -1. this doesn't care about W2, so you might as well just set W2 equals -1 there, at least for that part of it. Yeah. Okay.
We've seen like a bunch of loss functions. Like when you are picking one, like do you try a lot and then pick one, or like how do you pick a function in general? Like how much impact does it have which function you pick on like the application that you're trying to, the system you're trying to build?
Right. Yeah. So the question is, how do you pick a loss function, and does it have impact? It certainly does have impact. Some of it's chosen out of mathematical convenience or computation convenience. For example, we saw that if you want to choose a hinge loss, that's preferable than choosing the 0-1 loss because you can't optimize it. In other cases, you might have domain knowledge about some losses being more hurtful than others. For example, spam versus no spam. It's probably really bad to have an important email go to your spam folder, and the loss for that might be 100 versus if you get annoyed by a spam coming into your inbox, it's probably a loss of 1. So sometimes there's asymmetries in the loss. Yeah, one more.
Can you have a negative loss, or is loss always positive?
Yeah, so can you have a negative loss? Generally, we'll say that the loss is non-negative. Yeah. Okay, so let's move on. So this is all about just setting up an optimization problem that captures what type of predictor you want to find based on the training examples. So how do we actually optimize this? So last time we looked at two algorithms. We looked at gradient descent, which basically iteratively starts at a data point, not a data point, a point, let's say 0 here, and it computes the gradient, and then moves an eta step in that direction, and then computes the gradient again, and then eventually, under some condition, you'll converge to the optimum. We also looked at stochastic gradient descent, which is for the impatient. If you don't want to sit here computing this gradient, which is a sum over all your training examples, you can just take one example and compute the gradient, and on kind of average, you're going to move in the right direction. Right? So in this case, what does this mean? That means you're going to pick one of these examples and move in that direction. So you might be starting out, and you might pick this function, and you're going to move there. So clearly, that's not the right direction because you want to head more towards 3 minus 1. But notice that it's still kind of moving in the right direction. And so maybe you can kind of convince yourself, at least on this example, that if you kind of stochastically just take a gradient step, it'll be OK. But the formal justification, I think, is outside the scope of this class. And just to kind of remember, I coded both of these up. And stochastic gradient descent, at least on the simple example I tried, was much, much faster than gradient descent. So you can hope for many more gains if you make many more updates. But you have to be careful. OK, so let's move on with what this class is going to be about. So we're going to turn to the issue of features. Kind of thinking about how domain knowledge can help us explain the features, and then we're going to talk about how you might be able to build more expressive classifiers than linear ones on top of those features, and then we'll go from there. Okay, so remember there's the key kind of crux of prediction is the score function, right? And the score function is simply a dot product in a class of linear classifiers between the weight vector and the feature extractor phi. Okay, and so far we've focused on what happens if you hand me a particular phi of x. We've just assumed that it's fixed, and then we're looking at how we should learn w based on data. How do we set up an optimization problem, and how do we optimize it? Okay, so now what we're going to do is leave w aside and focus on what phi. In some sense, you could argue that phi is actually the more important of the two, but the less kind of well understood, and it's more of kind of an art, if you will. And this is where kind of domain knowledge has a big role to play. Okay, so the first order of business is to have a way of even talking about features. And this section might be a little bit kind of administrative or pedantic, but I think when you're kind of communicating about what features you're using, it's really important that we're kind of on the same page with respect to how the vague notion of features maps onto the mathematical notion of features. So we're going to talk about this idea of feature templates. Okay, so consider this familiar task of predicting whether a string is an email address. Okay, so you have a string, and so far we just went and last time just wrote down some features, whether the length is greater than 10 or so on. And this is pretty ad hoc, right? Why do we have contains at but not contains question mark or something? So we need a kind of an organizational principle, some way to think about creating not just one feature, but a kind of a set of features. So this is the idea of feature templates. A feature template is just a group of features all computed in a similar way. So often people, when they say features, they actually mean feature templates. But I think I want to make this term a little bit clearer. So here's some examples of feature templates that you might want to invoke for this particular task. So length is greater than underscore. So we're going to use this notation in this class to denote feature templates. And the way to read this is that length greater than underscore blank means that you can replace any value of blank, any value into the blank. So for example, this it kind of expands to length greater than 1, length greater than 2, length greater than 3, and so on. Right? So this feature template actually gives rise to multiple feature templates, which are all kind of related in some way. Another example is contains character A, contains character B, and so on. Okay? And so this feature template specifies a set of features. Each feature, for example, contains character A, is the name of the feature, and the value is something like 1 or 0. Okay, so just to make this kind of very clear, you have a feature like contains. So this is the feature template. Feature template. This is a particular feature, contains, let's say, A. So this is a particular feature, and we're going to think about this as the name of the feature. And then whether it contains A or not, let's say it does, then it's going to be a 1. And this is the feature value. Okay, just kind of a little bit pedantic kind of notation, terminology. Okay. All right, so here's another one, which is kind of common in vision. And in vision, I guess you start out with things that look like they're already vectors, so you don't really pay attention to this, but in this framework, you can think about it as follows. So if you have an image, you can think about the pixel intensity of position blank, comma, blank as a feature template. And this gives rise to the number of features equal to the length by the width of the image. So for every position, let's say 13, comma 20, you have a particular value, which might be, for example, a number between 0 and 1, which is the intensity of that position. All right, so here's a concrete example here. If you have feature template last 3 characters equals blank, then it gives rise to all these different features. Okay. So one note is that you can easily see how if the number of values of blank is really large, you could have a lot of features. For example, even last character equals blank. Right, you might have 26 different features, but notice that only one of them is going to be 1 on any particular example. Okay, so it's kind of inefficient if you have to kind of explicitly represent this in code. So let's talk briefly about feature representations. So there's 2 representations you can think about in code. So the first is array representation, and this is the one that we've kind of implicitly worked with. So remember the first lecture I told you that here's a feature vector. It really has names, but from the purpose of the machine learning algorithm, you can just drop them names, and now you have a list of numbers, right? And so that is the kind of the canonical way to kind of deal with things. But as we mentioned before, this can be really inefficient if you have feature templates that give rise to a lot of features, very few of them being 1 at any given time. Right, so array the representation is great if you have, for example, pixel intensity because it's a feature template, one feature template, but it gives rise to a bunch of features, but every position in the image does have a value and probably a non-zero value. But for usually kind of text data, where you have features of the form, contains a string or contains a word, you really want to use something more like kind of a map representation, which you can think about as a dictionary mapping the feature name to the value. Okay? And the implicit assumption here is that if a key does not exist, if a name doesn't exist in the dictionary, its feature value is 0. Okay? So if you have a lot of zeros and you don't represent them, then you're saving a lot. Okay? And this is a representation that you're going to look at in the sentiment homework, which is out right now. So let me just pause for a second to make sure everyone's questions are answered, if there are any. Yeah?
So for like contains alpha, it's not going to be there if it's value is 0, right?
Yeah, so
could you set like a set for it instead of like a map?
So I see. So the question is, contains alpha, should this be a set instead of a map?
Yeah.
So if all your feature values are either 1 or 0, you can represent it as a set. But often you want the flexibility of having other numerical features. And sometimes you have, like, for example, count features, which it's 1, 2, or 3. So it's a multi-set at least. OK. All right. So I'm going to, any other questions before I move on? OK. Yeah?
Can you use map representation when you're actually doing the algorithms, or do you have to like transform it at some point?
Yeah, so the question is, can you use the map representation when you're actually doing an algorithm? You can absolutely use the map representations. And in fact, in the homework, you're going to use the map representations. Yeah. Just a kind of a fun fact is that we think about vectors in this class kind of concretely as lists of real numbers, but there's kind of a more abstract notion of a vector. And a map actually can have properties mathematically as a kind of abstract vector, which means that you can not just like, it's not a kind of implementation trick, but it's actually mathematically doing the right thing, but outside of the scope of this class. Okay, so that's feature templates. And the second notion I want to talk through is that of a hypothesis class. And this is really the way I think it's productive to think about what a feature vector is doing. Okay? So recall that a predictor, in the case of regression, is this should have a f of x here. So this is either going to be the score or the sign of the score in the case of classification. Okay, so we can think about the hypothesis class is a set of possible predictors, assuming you have a fixed feature vector, but you vary the weight vector w. So think about ranging w over all possible weight vectors and looking at the types of functions you can get out. Okay, so let me make this clear in a simple example. So suppose we're doing linear regression in one dimension, which means that x is in R. So suppose we, okay, so let's see. So let's say phi of x equals x. So we're doing regression. And in this case, f of w of x is simply going to be wx. And there's no dot because I'm in one dimension, so it's just simple multiplication. OK, so fixed feature vector, range w, and see what kind of functions you get. So what are the axes here? So this is x, and this is going to be, well, y, or let's put w, fw of x, OK? OK, so what does this look like? So w is 0, that's the 0 function. If w is 1, then it looks like this. And you can see basically the set of functions you can get are linear functions that go through the origin. Okay? So every time you see phi of x equals x, you should think, well, this is the implicit set of functions that this feature vector is defining. or this feature map is defining, right? So it doesn't include functions that are squiggly. Okay. Question.
The function is defined by f, though you're not phi, right? Like the lines are defined by the weights, like the fact that you're saying the hypothesis is w times x.
Yeah, so the lines are defined by weight. So this line is w equals 0, this line is w equals 1, and so on. Okay? All right. So that's a notion of a hypothesis class. And here's the kind of the grand way to view things. There's a typo up here. So think about all possible predictors. These are all possible functions, including like cosine and all sorts of weird stuff. Every time you define a feature map, feature extractor phi, that's committing yourself to a particular subset of functions that you're going to entertain, right? So what you're saying is basically, remember, phi is supposed to represent the things that might be relevant for predicting x. It's not everything. So based on your choice of that, you're basically saying, I only think that these functions are going to be reasonable ones to consider. So that's feature extraction. And then the second part is learning, which is when you're doing learning, you're effectively selecting a predictor from this fixed set of functions, right? You're not able to select things out here because you've already committed to phi of x. Okay, so we've decoupled the problem into feature extraction based on domain knowledge and learning based on data. Okay, so let's explore what other functions can we create. Okay, so now we're going to get closer to answering the circle question from the beginning. So we already saw linear functions. So phi of x equals x, and that traces out what's on the board here. So this is just notation for what I said. So this means, think about this as like a lambda function in computer science if you want. So this is a function that takes an x and returns w1x. And this notation says I'm ranging w1 over all possible real numbers and take the set of all those functions, that's f1. But in some cases, linear functions aren't good enough. So for example, if you wanted to predict, let's say, someone's health based on their body temperature or something, it's not linear. It's not the case that the greater the temperature, the more healthier they are, or less the temperature, the more healthy they are. It probably needs to be some function that has some peak at I guess 37 Celsius and then tapers off somehow. Okay. So, so we can get at that by defining a different feature map. And let's suppose we define phi of x equals x and x squared. Okay? So what kind of functions does this give us? Yeah. So it gives us quadratic functions that go through the origin. So they look like this. They look like, I guess they can look like this too, and so on. Do they also include linear functions? Yes, because you can always have set w2 equals 0. So they also include linear functions, right? Okay. So I thought I'd shut this off. Okay. So these are quadratic functions, and they are a superset of the linear functions, because the linear functions you can think about the same thing as the same functions as quadratic, except for w2 equals 0 if you want. Okay, so quadratic functions are more, expressive, and notice. Wait a minute. So, we were looking at linear predictors, right? But so how all of a sudden are we talking about quadratic functions? And that's because, as we'll see later, that there's a question of what linearity means here. I'll defer that topic. Okay, so you can go a little bit further. So in this case, well, this is probably not actually a good predictor of health either, because it's not the case that, I don't know, well, it depends on how you're even measuring health, but you probably don't want a quadratic kind of decay. So one common trick you can do is this discretization trick. So it's really useful. So let's do it over here. So this is quadratic. So this is discretization or piecewise constant. And the idea here is that I'm going to define a feature map phi of x, which is going to be, now bear with me, so this is an indicator between 0, x less or equal to 1, indicator of 1, x between 1 and 2, and so on until maybe, let's say, 9 and 10. This is a little bit arbitrary. You can pick other values here. Okay, so what does this give you? So what is this saying? This is x, remember, is a number. And I'm going to map it into a 10-dimensional vector. And the vector is going to be 1 at a particular point, which is the interval that x falls into. Okay? So it's going to be 1. This is going to return 1 if x is between 0 and 1. And this is going to return 0, and so on. Okay? Okay, so what this is doing is it basically is chopping up the x here. So this is still x. Into, let's say, 10 buckets. And remember, for each region, I have a weight associated with it. And so what is an interpretation of this weight? Anyone? Yeah.
What range x should be in?
Yeah. So the weight. So let me write it out. So the weight, it has to do with the particular feature, but what is its interpretation? So w f of x is equal to. Let me just write it out kind of manually. Okay. So this is 1, and so on. So the weight is a coefficient on top of that. So if x, for example, is 0.5, what is the function value here? W1, right? So in some, effectively, the weight is, this is W1, and then this is a W2. So the weight controls essentially what the function value of the function in that range is. Okay? And because you can vary the weights however you want across the 10 buckets, you essentially can define any sort of piecewise constant function you want on this discretization. Yeah?
Variables and features?
Yeah, so there's a note so the question is, how do you extend this to multiple features? And that's a good question. So the notes talk about this briefly. You can do it. So what you would do is basically define the regions to be x1 is between this range and this range, x2 is between this range and this range. So you can define it. The problem is that if you think about the number of regions in, let's say, d-dimensional, it's exponential in d. So the number of regions is too big, and you probably wouldn't want to do that. So this is typically good when you have a small number of features that you want to discretize. Okay, so this is in some sense a very classical trick. You'll probably kind of encounter it and use it. It's independent of whether you use neural nets or linear classifiers. It's whenever you receive an input which is a real value, but you expect that real value to contribute kind of very differently to your function depending on what range it is. Then you want to discretize it because then that gives you the flexibility of associating a function value with each particular value. Okay, so now we come to a question, linear in what? Right, so remember the prediction is driven by the score. So is this score function linear in W? How many of you say yes? Okay, it is. What about linear in phi of x? What about linear in x? No. And in fact, it doesn't even make sense. So the way you check is that you think of x as a person. And what does it mean to be linear in a person or a string or something, right? And this is a key point, is that when we think about these decision boundaries, here x is a number, but it gets to go into this feature vector, and we're linear in the feature vector space, not in the original space, where in general it might not make sense. Here you can think about it type checking, but it doesn't have to be linear in x. Okay? So this is really cool, right? Because you can, so these predictors can be really expressive nonlinear functions of x when x is a real vector. But at the same time, when you talk about learning, you don't care about any of that stuff. Someone just hands you phi of x and it's a vector, which means that you can just focus on linear classifiers and do efficient learning without having to worry about curvy things. Yeah, question?
You're saying that x is an input, like it's some abstract thing. I'm a little bit confused about how that matches up with what you're doing on the board. Like, is this an analogy, or are we actually taking x to be a real number?
Yeah, good question. So what does it mean when I say x is this abstract thing like a person? So in this case, this is not just, this is a real example, and sometimes your x is actually a number. In that case, it makes sense to think about, is this function linear in x? And in this case, it is. In these cases, it's not. In other cases where x is a string, for example, an email address, it doesn't even make sense to ask the question, is the function linear in x, because x is a discrete object. And in that case, you can still map x, a string, into a feature vector, and then the functions are linear in that feature representation. Okay, so here is this circle question again. So here, if we wanted a decision boundary in 2 dimensions that separates the circle from everything outside of it, how would you define the feature vector? So borrowing an analogy from the kind of the quadratic case, you can define your features as 1, x1, x2, x1 squared plus x2 squared. So the details, how I got this isn't so important, but the point I just want to stress is that if you define it in this way and look at linear classifiers on this phi of x, you can get these circles. So let me show you this video, which I think helps illustrate this concept. Okay, so this is something that was done in the context of SVMs, but the same idea applies here. Okay, so here we have you in 2 dimensions. Is this plain? Okay, I don't know what's going on. Okay. So in 2 dimensions, they look like you basically have this points in a flat grid. And what phi of x is doing is it's lifting the points into 3 dimensions in this case. And in 3 dimensions, you see that you can fit a linear classifier that separates the pluses and the minuses. And that looks like a circle. So if you go back to 2 dimensions now, you get this circle. Okay? You want to see that again? I thought that's pretty cool. Okay, so remember you have points in 2 dimensions, and you're thinking like, oh my God, how do I separate the positives and negatives with something that looks like a slice? And you can't. And the key is that by defining these feature vectors, you can kind of transform your data, in particular into high dimensions. So now in high dimensions, there's kind of more space, and you can take your knife and slice the data. So that's a picture you should have in mind. Yeah, question?
It's still going to be 2-dimensional though at the end.
Sorry, I can't hear you. Can you speak up?
Well, the classifier will still be in the same, eventually be in the same dimensions as the input data, right? Essentially.
The classifier is in the same dimension as the input data. Depends on what you mean by the dimension of the classifier. So the function you get out at the end of the day is still a function that takes the input data, which is in the low dimension, the original number of dimension, and makes a prediction. So from the outside world, the outside world doesn't have to worry about whether you're imagining like this really fanciful high-dimensional space. But internally, what's going on is that you're living this high-dimensional life. Okay, so let's move on. So let's kind of wrap up. That's all I'm going to say about hypothesis classes and feature templates. So let's wrap up a little bit by thinking about how, just kind of a little exercise to think about how we might design features. So here's the prediction problem. So the motivation for this is that you're chatting either in Facebook Messenger or Slack or whatever, and you often see these long chains, and you really like to kind of group the long sequence of messages into threads or conversations, right? And so the goal is, given 2 consecutive messages in a chat, you want to predict whether the second one is a response to the first or not. Okay? So might be an interesting project idea. I don't know. So recall that the feature extractor should pick out properties of X, which might be useful for prediction, and we need to return a set of feature value pairs. Okay, so let me do this kind of exercise. This is, sorry, my internet is not loading. But let me walk through this while I'm waiting here. So what feature templates would you use to predict whether the second message is a response to the first? I don't know. I have to like reset a bunch of things. Okay, time elapsed between the sent times of the 2 messages. Time elapsed between a particular range. First message contains a particular word. Second message contains a particular word. Or okay, I don't know why my internet is not working. Okay, I guess we'll do this kind of old-fashioned way. 2 messages can both contain a word, or 2 messages have n words in common, like 1 or 2. Okay, so how many of you think the first feature is a good one to use? Time elapsed. Okay, how many of you think the second one's a good feature to use? How many of you raised your hand twice? So let me comment on this first. So time elapsed, this is definitely important information, right? So you imagine if time elapsed is, let's say, a day, then there might be probably different conversation threads. But if you put time elapsed into a feature vector, now you're implicitly making some sort of linear assumption, which means that the longer the time is, the more likely the prediction is going to be one way or another. So which means that if you wait a day, that's going to be way more likely, let's say, to be different than let's say, I don't know, 5 minutes or something, right? So, and this might be a bad assumption because the length of time doesn't really relate linearly to your kind of prediction score. So typically when you have a number which has a very high dynamic range, you generally want to bucket it into ranges. So you can chop it into these discrete regions like we did a moment ago. And that corresponds to this feature vector, time elapses between X and Y. Okay, so what about first message contains a particular word? Okay, what about second message contains a particular word? Okay, so these are, there's no right answer here. So it might be that this is useful. It might be the second message is useful. And you can probably toss both of them in without kind of hurting things too much. One thing I should stress is that when you're thinking about classes of functions, it's okay if the vast majority of those functions in your hypothesis class are bad, right? So if you're fitting a line, this line and this line can't possibly both be good. But it doesn't matter because the job of learning is to choose the appropriate function from your class. So one thing to remember here is that if you're just adding a feature by looking at the second message, it's really looking at, well, are certain words more just on their own indicative of a conversational thread or not, right? What you don't get is the interaction between the first and the second messages. So this is another kind of potential failure code where you're just tossing in features into a linear classifier, but you really have to look at them kind of jointly, which is what the last two features are doing. However, at the same time, you might imagine there's some signal. For example, if the first message ends with a question mark or something, maybe it is more likely that the second one's going to be a response, but not always. And the second message alone might give you some clue. For example, if it's like hello or something, maybe it's not likely. But if it's I don't know, sounds great or something, maybe it's more likely to be a follow-up or something. So there are individual cues. But one thing I want to point out is that when you look at a feature, you have to think about how does this, in the context of a linear classifier, how does this feature kind of directly impact the prediction? And sometimes you need to look at the conjunction of two features. Okay, so that's all I'm going to say about this. So any questions before I move on? All right, so summary so far. We looked at feature templates. These allow you to define large collections of features in an organized way. Hypothesis class is really what you should be thinking about when you write down a feature function. What are the possible functions I'm considering? And then this kind of a really nice and surprising fact, perhaps, about linear classifiers is that they can actually represent pretty remarkably expressive classifiers. Okay, so now I'm going to go on to neural networks. And this is just going to be the kind of the very basics. There's a lot more to be said about neural networks, but I think this is going to give you kind of the some of the basic knowledge. Okay, so many of you probably have heard about neural networks and all the great things they do. One thing I want to try to do is kind of build up using a simple example and try to motivate why they might be a kind of a reasonable thing to do. So the motivation here is going to be, a little bit, shall we say, a little bit kind of, I know it's a toy example and it's a little bit kind of fanciful, but hopefully the bigger message will, stick. Okay, so suppose you wanted to solve the following task. You want to predict whether two cars are going to either crash or not, or be safe or not. So the situation is as follows. You have this road here, and you have a car that's going this way, and it's at position x1. And then you have another car going the opposite way, and this is at position x2. And the question is, are they going to collide or not? Okay, or whether it's going to be safe or not. So +1 is good, -1 is bad. Okay, so here's where it's a little bit of a fanciful story. Is that we're just going to assume that suppose out there in the real world, the true function that we're trying to estimate is they're safe if the car's distance is at least 1 apart. Okay, so normally you wouldn't know if you're doing learning, you don't know the true function, but I'm just going to kind of go through the thought process of say we did, then what would happen? Okay, so if x1 is 1 and x2 is 3, so that's like if you're, I guess, driving in the UK, then that's fine. So if x1 is 3 and x2 is 1, that means you're driving in the US, and that's fine. And this is where you're driving in probably some place that doesn't have good traffic laws, and that's bad. Although they somehow manage to avoid collisions sometimes. Okay, so this is kind of set up clear. You're given x1 and x2, you're trying to predict y, and we're just going to assume that this is the kind of the right answer. Okay, so how would you go about doing this? So first of all, it's it's not. This is not a linear, prediction in x1 and x2. So if you threw in x1 and x2 into a decision boundary, into a classifier, you wouldn't expect to see good results. I mean, just to kind of show what this looks like, right? So x1 and x2, and what you really have is a, what does the decision boundary look like? So this region is going to be plus, because x1 and x2 are far, and the middle region is going to be minus. Okay? So then you say, wait, well, we just went through 30 minutes of saying how you can design features to basically get decision boundaries, which are circles, and probably you can do something like that too. It's all true. But we're going to try to see how we can maybe automate this process and not have to go and design features for kind of every specific case. Okay, so the key idea here is decomposing the problem. So let's try to break this down into first let's test whether car 1 is to the far right of car 2. So that means x1 is greater than x2 plus 1 by some plus 1. Okay. So that tests whether you're in the kind of this lower region on the board there. We can also test if car 2 is the far right of car 1. Okay. Just flip x1, x2, and we're going to declare it to be safe if there's at least one is true. So you look at h1 and h2, both of them are 0, 1, and if at least one of them is 1, then we're going to predict 1. If both are 0, I'm going to predict minus 1. We're just going to assume that sign returns minus 1 for input that's 0. Okay, so what I've done, I mean, this is maybe a little bit, seems a little bit gratuitous, but I've basically written down the true function as kind of decomposed it into different pieces. Okay. All right, so on these particular examples, 1, 3 gives you x2 raises its hand and said, car 2 is a far right of car 1, and that's enough to make y plus 1. For 3, 1, h2 is 1, h1 is 0. H1 is 1, h2 is 0, and you get a plus 1. And in this case, both are 0, and you get a minus 1. Okay. So this is all if you knew the true function. But let's take this kind of general idea of decomposing the function and see how we might be able to represent this as a neural network. Okay? So the first thing we're going to do is we're going to define a feature representation. Phi of x equals 1, x1, x2. And now we can write at h1 and h2 as in this following form. Okay? So we have a weight vector v1, minus 1, plus 1, minus 1, and dot with phi of x, that's just to do the algebra on the board here. So if you have 1, x1, x2, dot with, so the v1, so this is minus 1, plus 1, minus 1. So this is going to be what? This is x1 minus x2 minus 1. Okay? So this is what goes into the inner expression here. I'm testing whether that's greater or equal to 0, which is exactly what I have here. Okay? So I'm just rewriting the kind of the solution in terms of these dot products. Okay? And then finally, this part is kind of the easy part. So how do I get sine of h1 plus h2? Well, you set w equals 1, 1, and then you put this weighted combination there. Okay? Okay, so now comes the kind of the actual learning part is, we've gone through the motion of saying, hey, if your true function was like this, then you would set the weights somehow. But remember, you don't know the true function. So what we're going to do is we're just going to say, well, there's some v1, v2, w. I don't know what the values are. But I'm going to try to set them based on learning. Okay? So this is kind of really a thought experiment here. So suppose we knew the function, true function, we could design a kind of a model that looks like this. And now we say, hey, we don't have the true function. Can we try to learn this? So this is trying to just motivate why this kind of particular form might make sense. So what we're trying to do really is we're trying to both learn the hidden subproblems and the weights at the top at the same time. Okay? So any questions about this?
Assume you know there.
So the question is it a general strategy to assume you know and then work backwards? It's a strategy that works in some cases where you're basically trying to think of kind of a simplified case where you might be able to have an analytical solution, and then you look at what the solution should be, and then you kind of relax a little bit and say, well, this number I used to set to -1, but I don't actually know what it is. Let's just make it a parameter. So the short answer is yes, and the strategy you can think about is try to write something down that is the solution, and you don't have to get it right, but if you can isolate certain things as parameters which you don't know the value of, then you can let learning take over. Yeah, question?
What does V1 and V2 represent again?
Okay, so what does V1 and V2 represent? So these are the wave vectors that are responsible for solving this quote-unquote subproblem, right? So H1 is the value, you can think about it as an intermediate classification problem that says, is car 1 to the far right of car 2? It's not the full classification problem, but it's an intermediate problem, and V1 are the weights for that. And V2 are the weights for the other subproblem. And having solved those subproblems now W is the weight vector that's responsible for combining those solutions into the final answer. Yeah, question over there.
Ultimately, are we going to get to a solution that is us saying what the subproblems are, or are we going to try to learn on, there's this wide space of subproblems, let's just learn and try to figure out which representation of subproblems makes the most sense?
Yeah, so I think the question is surrounds do we maybe know what the subproblems are? And the answer is no. So when you give up control to a neural network, it's going to find whatever subproblems it deems fit to actually solve the problems. And later you can go and introspect and you say, oh, well, this neuron kind of detects edges like these and so on. But a priori, you have kind of little control over that process. What I'm doing right here is trying to motivate what these subproblems might look like in a very kind of analytical setting to kind of, I don't know, stimulate your imagination. Because otherwise it's just like, okay, well, there's a neural network. It computes some random value here and random value here. Like, what does it mean? So I'm just trying to add some color here. Okay, one more question and we'll move on.
Are the values for all the weight vectors arbitrary, or did we derive them?
So the question is, are the values of these wave vectors arbitrary? We're going to actually learn them from data. So here I've set them to particular values because we pretended we know what the truth was, but we're not going to in general. Okay, so speaking of learning, the classic strategy is to use gradient descent or stochastic gradient descent, but we immediately run into a problem here because if you think about the gradient of H1 with respect to V1, this is basically 0 all the time, right? So, if you have this plot here, so this is on the x-axis is going to be v1 dot phi of x, and the y-axis is going to be h1. So what this looks like is, it's going to be 0 up until this point, and it's going to be 1. And just like we had issues optimizing the 0, 1 loss, you also can't optimize this. Because if you're here, then it's like, OK, well, no matter how I change my weights v1, nothing's going to move, so I'm just going to stay still. OK, so how do we get around this? One of many solutions is to try to smooth out this function a bit. So there's something called a logistic function, which looks like this. It's 1 plus e to the minus z inverse. And pictorially, what the sigmoid function looks like is it looks like this snaking s, which is half here, and it goes to 1 and goes to 0, but never reaches 1 and 0. So this is sigma of v1 dot v of x. Okay. And the property that the sigma function has is that it's differentiable everywhere. So if you're here, there's a gradient. If you're here, there's a gradient, and so on. Which means that we can take the derivative and we get some value which is not going to be 0. So just a kind of a side note, sometimes it's really small. So over here, the gradient is pretty close to 0, and that causes some problems, which we can talk about later. But if you're in this kind of region, then the gradients are not 0. Okay, so if you go, and everyone should go do this, take this derivative of this, then you get this particular form, which looks pleasing. Okay. All right, so let's just replace this hard threshold step function with the sigmoid function. Okay, so now we're basically ready to define our neural net. So we're going to draw in a particular way. So remember linear predictors. We can think about the inputs as multiple components of this feature vector, phi of x, all feeding into, with weights w into the score function. And that outputs this dot product. So this is how we're going to visualize a linear predictor. Okay. And a neural net is a 2-layer neural net. It's just going to be represented as follows. So you start with the same feature representation. And now you're going to first compute these intermediate units, hj. So here's 2 possible intermediate hidden states here, which is the same thing that we saw before. You can think about these as solving subproblems. And then you take a linear combination of these, w dot h, which is the vector of these activations, and that produces your score. Okay? So these equations here, the hj and the score, is a full specification of what a simple 2-layer neural network is doing. Okay, any questions about this? Yeah.
Why don't you use the logistic expression for the last score?
The question is, why don't you use the logistic for the last score? You could, depending on what you're trying to do. If you're trying to do regression, then you want the score maybe to be some arbitrary real value. Whereas the logistic basically outputs numbers between 0 and 1. So if you wanted a number between 0 and 1, you can always apply it here as well. Yeah.
What does the phi sub 1, sub 2, sub 3?
So what does a phi sub 1 mean? So phi of x is a vector, and sub 1 just means the first component of that vector. 2 means the second component as well. Okay, so let's move on. So the neural network, here's one way to think about what it's doing. So remember, before what we were doing is we're taking a linear predictor on these manually specified features, phi of x. Okay. Now you can think about the neural net is also, in some sense, a linear predictor, but on learned features. So the learned features meaning h1 through h2, h3, all the way to hk of x, right? So these are not fixed, they're learned. So if you look at this diagram, this bottom equation looks like the expression for just a linear classifier. But the thing is that h is not a fixed function. These are parameterized and they depend on the v's. So a neural net in some senses you can think about as doing feature learning. It's trying to learn features with respect to a linear classifier. Of course the neural net is still going to start out with v's. So whatever domain knowledge you have, you should put it in and set it up that way. But the neural net can kind of do additional work on top of that. Okay, so now we've set up what a neural network is. How do we actually algorithmically learn one? Okay, so this is nothing new. What we're going to do is do loss minimization, right? So when I said loss minimization was a general principle, I kind of meant it. It kind of works no matter if you're learning linear classifiers or neural networks. So it's going to look like this. So minimize the training loss, and now there's two sets of parameters. There's the weight vector at the last layer, and then these v's, v1 through vk. And what is this? This is the same as before. This is the average of all of the loss functions of individual points. What is the loss? Well, if we're doing regression, then as a square loss, it's y minus the predictive value squared. What's of fvw? This is the neural net has this form, which is this is just writing out the last layer. It's a summation over all the kind of intermediate steps, hidden activations of wj times sigmoid of vj times vx, v of x. Okay, and then you just have to compute the gradient of this expression. So now this looks like a lot of symbols. It's conceptually not that bad. Hopefully you agree with me. But if you want to, if I handed you this on compute a gradient, you probably do a page of algebra, and then you'll hopefully you don't make any mistakes, and then you're good to go. And if you have a bigger neural network, you can just do 2 pages of algebra, and then you're good to go. So one thing you can do is I'm sure all of you today you can just go and grind through the change rule, and you'll be good. But what we're going to do next is show you a way of visualizing this computation in a kind of in a more intuitive way. And the advantages of this is it allows you to kind of literally see kind of what is going on when we're talking about these gradients, avoiding these long equations. And also, this is not so much for you, but for people who make TensorFlow thing, it actually allows you to kind of see the structure of these computations, and you can design generic algorithms such that all you have to do is write down the model, and the algorithm can automatically compute the gradient for you. Okay, and this is done for all of these kind of popular neural net packages like TensorFlow or PyTorch. Okay, so in some sense, you can get away these days without actually knowing how to compute a gradient, but it doesn't hurt to practice. All right, so conceptually, what is a function, right? So if you back to this, train loss is just a function, right? It may be really complicated, but it's just a function. And a function is something that just takes inputs and produces output. And so what are gradients? They're just basically kind of a sensitivity analysis. It's like saying, if I change one of the inputs, how much is the function value going to change? And this is really important to keep in mind as you're doing these. I hate to see people kind of doing lots of algebra without understanding kind of the principles here. So for example, if you have this function, which is 2n1 plus n2 n3, what happens is, so if you want to compute partial out of n1, you think about what happens if I add an epsilon into the input 1. So epsilon, think about it as a small positive number. And you can do the math and you say, output's a 2 epsilon. So for every epsilon you put in, you get 2 epsilon. So the partial derivative here is 2, right? Okay, so what happens if you add a little epsilon into n2? Then you get out an n3 plus epsilon, and this is just normal standard algebra. And so the partial derivative with respect to n2 is n3. Okay, so you kind of get the idea. So when in doubt, you can always go back to these kind of first principles and think about intuitively about what a gradient is supposed to do. Okay, so what we're going to do now is to so this is kind of just some arbitrary function, right? But it turns out that most functions that we care about can be basically broken down into a bunch of basic building blocks. Okay, so I'm going to talk about 5 of them here. And these are kind of plus, minus, times, max, and the sigmoid are going to be 5 building blocks. So this function is a plus b. And so let me do this on the board, actually. So what is the partial derivative with respect to a? What should be here? 1, right? And this should be 1. Okay, because if you increase a by a little bit, this is the same stuff just goes through the top. Okay, what about minus? Someone say minus 1 times. This should be, if you put in a, then it gets multiplied by b, and then this is the symmetric case, and max. So this is a little bit more interesting. So what goes on this edge? Indicator of a greater than b, that's right. And the reason is that when a is larger than b, then if you change a, then this is just going to send a 1 through. But if it's less than b, then whatever you change here doesn't have any effect. So the effect, the partial should be 0. And analogously, this is b greater than a. And then finally, sigmoid that takes an a. What is this? It was on a previous slide. Sigma of, let's write a of 1 minus sigma of a. Okay? Okay, so now we have our tools. And the claim here is that this is all you need to differentiate kind of a lot of different things. Okay, so that's, so one other ingredient is that if you're composing functions, so suppose I take an input and I send it into one function and then it goes into a second function, what is the partial derivative of out with respect to in? It's just the product of the partials. Okay, so if there's a gain of 2 here, for every unit you put in, you get 2 out, and then for every unit of 1, you get 3 out, then you get, for every unit of 1, you get 6 out. So that's kind of the intuition. Okay, so let's do this kind of example for binary classification with hinge loss. So remember, this is the loss, and we did this last lecture, but here's what it looks like in this computational graph form. Okay, so this function is w dot phi of x, that's the score, times y, that gives you the margin. And this is 1 minus the margin. You max it with 0, and that gives you the hinge loss, right? Okay, and now you can apply all of these rules, and you say, okay, well, the max of these arbitrary 2 things. One is what's going to go on this edge. It's exactly the indicator of the left expression greater than the right expression. This is minus 1. You can read it off the board. This side is the right argument, which is y. This side is the right argument, which is phi of x. And then you just multiply all the edges together, and that gives you the gradient of the loss with respect to w. Okay? So I personally like this as a kind of very visual way of thinking about how kind of gradient flows, so to speak. Any questions about this before we move on? Okay, so we can do something a little bit more complicated. So here's a neural network for a single example. Same idea. What is a squared function? I guess this is a rule that we didn't exactly have, but you know what the derivative of a square. It's 2 times the input. And this is a 1, this is 1, and I guess you can kind of trace. So now, if you wanted to take the derivative of W1, you just multiply all these edges. If you want to take the derivative of V1, you multiply all these edges together. Okay? So one thing you might notice is that the derivative for V1 and W1 have some shared structure together. They have common expressions. So maybe we can try to leverage that. So this leads to what is typically called the backpropagation algorithm, which is, you can think about it as algorithmic instantiation of a chain rule, if you like. And what we're going to do is we're going to define fi for every node in this tree as just simply the value. So this is a forward value. This is, this is the loss. This is the score, and so on. And and g of I is going to be the partial derivative of the output with respect to the particular node that you're sitting at. Okay? So, and this is how much, if I change a particular node, how much would it affect the output? Okay, so these are just definitions, forward and backward. And now backpropagation computes all the forward and backward values for every single node as follows. So first, it takes a forward pass, and this is just computing the function value. So you go from the leaves all the way to the root, you compute this value, that allows you to compute this value, which allows you to compute this value, and so on. And then the backward pass, you're going to compute each gi, which remember is expresses the partial with respect to that node against the output. And this can be done kind of recursively as follows. So if you have computed the gj, which is the partial of out with respect to node j, and there's an edge here, then gi is simply going to be this, whatever's on that edge, times whatever is at this node. Okay? So for example, if you have, if you want to compute the partial g of this value, then it's 1 times whatever value sitting here, which would be 2 times residual. Okay, so that's essentially the backpropagation algorithm. Any questions before I move on? Yeah?
Can you speak on what happens when you have the same variable in different branches of the tree?
So what happens when you have different variables so the same variable in different branches? So for example, if W1 occurs here and it happens to occur here. So you can actually more generically think about this as a graph. So they would be just one node. Yeah. Okay, so we had nearest neighbors planned, but I'm going to skip this in the interest of time. Maybe you can go over it in section. I guess I can't activate. Oh, I can't activate this. So if you guys want to put into the poll, what is the most surprising thing you learned today? Just to conclude, just a 1 minute. So we saw linear classifiers. They're easy to learn. The prediction is fast, but they're relatively weak in terms of the use of features. So you can produce really complicated features, but they're still linear on top of those features. So neural networks allows you to make more powerful use of the features, but they're harder to learn because they involve backpropagation and it's a non-convex optimization problem. But prediction is fast. And then nearest neighbors gives you a different trade-off, which we can cover in section. So that's all. Thanks.